So fellow member Bill Higgins graciously stepped in at the last minute to a presentation for us titled NASA's Psyche Mission, Electric Voyage to a Metal Asteroid. Psyche is the name of a new NASA spacecraft and also the name of its destination, a large, dense asteroid that seems to contain a lot of metal. No spacecraft has yet visited any of the iron-rich asteroids that are parents of the metal meteorites in museums. After launch this coming autumn, NASA plans to use electric propulsion to fly to Psyche, enter orbit, and study it closely to learn whether it is a core of a larger, shattered protoplanet. Join Bill Higgins for a look at the asteroid belt's latest explorer. Bill Higgins frequently speaks about spaceflight and astronomy. He works as a radiation safety physicist at Fermilab. He is pleased to have been an NAA member since 1989. He volunteers in NASA's Solar System Ambassador Outreach Program and was recently Science Guest of Honor at WindyCon, a science fiction convention. Please welcome Bill Higgins.
Thank you. Bill Higgins frequently spills water on himself, apparently.
And others.
I'll dry off during the course of the talk, right? Good evening. I'm pleased to be asked once again to address this great club, the Naperville Astronomical Association, this will be my second talk during the 50th year of the club's existence. So like that's my way of celebrating, I guess. And I hope you'll tolerate me, but my last time I was here a few months ago, I was talking about a flight to an asteroid, and I am talking about a different flight to a different asteroid tonight. So if you can, there are many things in the sky to talk about, but I guess in the year 2023, I'm the asteroid guy. I volunteer, as Kurt mentioned, in NASA's Solar System Ambassadors Program, where we don't get paid, but we agree to bring news of spaceflight and astronomy and perhaps NASA's work to our communities. And as such, it's an exciting time. Let me persuade you that it's a good year to be an asteroid guy. Because Psyche, the topic of today's talk, is going to launch very soon, but because recently we had a deliberate collision with an asteroid in September, the DART mission. The Lucy mission is on its way to the Trojan asteroids, in fact, both sets of Trojans and a few other little asteroids in between. The OSIRIS-REx mission, the American sample return mission, is on its way home from the asteroid Bennu, and it's carrying pieces that will land on Earth later this year. The Japanese have already done this trick with Hayabusa 2, and people are studying the fragments of Ryugu, the asteroid Ryugu in laboratories in Japan and other countries. The Europeans are getting close to launching Hera next year, which will return to the asteroid the asteroid pair that DART visited and follow up studying what the damage was and learn a lot more about those particular rocks. And there's a Chang'e probe planned by the Chinese, and it may fly and do a sample return some year pretty soon. So, like I say, it's an exciting time, and Psyche is one of the family of human spacecraft probes that are investigating various mysteries of the asteroids. In this case, there's an asteroid called Psyche, and they've named the spacecraft after it. So this is completely confusing. Okay. And Psyche's job is to fly to its asteroid, go into orbit, and study for a couple of years from orbit, and going into successively lower orbits as the months go on, to try to do different aspects of the science. For the briefings that I've gotten, and from which I've stolen a great number of slides, I should thank, first of all, the principal investigator of the Psyche mission, Dr. Lindy Elkins-Tanton of Arizona State. She did presentations for the ambassadors and for lots of other people. You can see some pretty good talks she has on YouTube. And Dr. David O of Jet Propulsion Laboratory was an expert on the engineering side who gave me a nice briefing. And Kay Ferrari runs the ambassadors program, and I'd like to make a nod to her. Dr. Elkins-Tanton has recently published an autobiography. So that is well worth looking at if you want to see how a young woman gets curious about science and a bunch of other things, and grows up to be a geologist and immerses herself in geochemistry and winds up as the PI of a space mission. A portrait of the scientist as a young woman. But to turn our attention to the spacecraft and its mission, Psyche is is going to a world which looks a lot like it's metal, or has a lot of metal content in it, and it may or may not have been created in a big bang, a small bang, I guess, a destructive collision that uncovered the deep part of a larger asteroid, or there might be other processes that led to the creation of Psyche. We don't know, but the project hired Paul Rubin, a commercial artist, to illustrate some of these scenarios and make nice pictures of the spacecraft and imaginary scenes of the stuff, science it's about to study. So you'll see some of his pictures here and there. Here's another Paul Rubin painting, I think. The spacecraft itself is a box with some solar panels on it and an antenna. You can, as so many interplanetary spacecraft are, the engines and the electronics and the power processing stuff and the thermal control stuff are mostly in here. There's a dish. It's you see it covered with reflective material here, but there's a dish-shaped thing under there somewhere, and this is going out pretty far into the asteroid belt. So it's going to the sunlight will be way less intense than it is here at Earth. So for spacecraft power, you need bigger solar panels, generally speaking. If your spacecraft is powered by an electric propulsion source, you need very, very big solar panels. Yeah.
If you're going to cover this, Bill, that's fine. If you're not going to cover it, my question is, how does one, while standing on the Earth, determine which asteroids are stony and which ones are iron or metallic?
Yeah, I wasn't going to go into that a lot, so it's a very good question, and I really should address it. You got a telescope. You look at most asteroids, almost every asteroid, and it's only a speck. You can't resolve it. It looks small, like the image of a star looks small, and very few asteroids are big enough that even the best telescope can see their shape. Okay, so all you've got is light coming from essentially one pixel to work with. I do have and for the case you're asking for, how do you distinguish between asteroids made of one thing and asteroids made of another? then that's pretty much spectral information. You hook up a spectroscope to your telescope, and you get a spectrum, and it's maybe it's strong in the red and weak in the blue, or the other way around. Maybe you can see bumps in the spectrum corresponding to wavelengths where certain kinds of minerals like to absorb light, or are not particularly good at reflecting light, maybe I should say, because what you're seeing coming off of an asteroid is all reflected sunlight, of course. Okay, so you know the solar spectrum, and whatever you get back from the asteroid is, subtracting light from the solar spectrum, and there are that being the case, you can tell the spectrum of something that's like a stone from the spectrum of something that's more like a metal-rich rock. And as a bonus, this is a general problem. We use spectroscopy to study galaxies and stars and molecular clouds and that kind of stuff. But in the case of asteroids, we have an ace up our sleeve, right? Because in museums, we have cabinets full of rocks that have fallen from the sky. And we're pretty sure that they came from one kind of an asteroid or another. So you can go into your chemistry lab and look at those rocks with a spectroscope. And meteorite spectra have families, and you can divide them into different classifications based on what minerals they have. And while it's not a perfect match and it's not an easy technique, what you learn about meteorite compositions from spectroscopy is very, very valuable in figuring out asteroid compositions. So a slightly long-winded answer to your question, but it's a deep question that deserves a long-winded answer.
Thank you, Bill.
Let's think about the early solar system. Once there was gas and dust, and some of it got a little closer to some of the other gas and dust, and we began to have an attraction toward the center that evolved into a whirling system of stuff. Okay, so that's the very earliest moments of what became the solar system, and we can look around us and see the present one that has a sun in the middle with almost all the mass in it, the big planets that consume that make up most of the rest of the mass, and lots of interesting small stuff like comets and asteroids also running around. How did we get from one to the other? What was the process of formation of the planets? That's always a big question. Or indeed the asteroids. And we think that planets came together because smaller bodies banged into one another and stuck, or at least portions of them stuck, and created. So studying the small bodies like asteroids, and particularly studying what you can of their history, helps give you a lot of clues to the formation of planets. And now that we have a few thousand planets in other solar systems where we can we don't have meteorites from there, and we can't see their asteroid belts very well. It's our asteroids are even more valuable in trying to put the pieces of this puzzle together. And indeed, putting pieces of the puzzle together, once some of this stuff is condensed in the colder regions, and the dust has stuck together, or maybe enough dust is stuck together that there's significant gravity, and we begin to get processes that compact grains of dust, or if it gets big enough, maybe heating. This is the early days, so there are more radioisotopes that haven't decayed yet in the early solar system than you find hanging around now, and they might be a source of heat. And what with one thing or another, some of the little rocks running around might be pretty cold and made of dusty stuff, but some of them might have gotten warm enough mostly through radioactivity, to have melted in their centers. And the smaller ones, as I said, can come together and make bigger ones, and that's how we get big asteroids like Psyche. But it's also true that these collisions, which are happening frequently in the first 100 million years or so, also will knock two rocks will hit each other. They'll knock pieces off, right? So you can shrink your asteroid as well by collision processes, and there's equations for both of those kinds of processes. Some more frequently than others, but in the simplest picture, or the explanation that's easiest to give to people about Psyche, there was some pretty big asteroid, say hundreds of kilometers across, and maybe 1,000, and it was warm, and it melted in the center, and the heavier materials sank to the bottom. Those are the metals, right? So you've got sort of like iron and nickel and stuff in the center, and stuff that's more like rock or magma that floats on the outside, so it's a little planet. They call it a planetesimal. And then some other big object came along and knocked this to pieces. And in this story, Psyche is the metal center that's left after the disruption of this larger parent body. Now, that isn't the only way. I don't understand all of the geophysics, but that's not the only hypothesis for making such objects. So Psyche may have evolved by a different process, and that's one of the things that needs to be investigated. Here's Stephen Rubin telling us, Peter Rubin, showing us about a disruptive event like the kind I was just describing. Maybe there was a big parent body, some small fast thing came in, and blam, lots of material got loose, and the heavier metal parts stuck around and accreted together, maybe also including some stony parts. This picture emphasizes what I was saying to you, that we really don't have information about what Psyche looks like. All these paintings are just kind of fanciful based on what we know about meteorites and asteroids. And here's a picture from a backyard telescope of the asteroid Psyche. I may not have said properly that Psyche is the 16th asteroid. It's the 16th asteroid discovered in 1852, when asteroids were pretty much a novelty, it was named after a Greek goddess. It is the largest asteroid of something that looks like metallic composition. I'm just going to zip through these. Yeah. And again, I alluded to this a little bit when I talked about spectroscopy. All you get is a little bit of light in your telescope from this object, or maybe some other tricks that you have for observing distant objects. But by combining one technique with another, I talked about spectroscopy already. Most people here know about light curves. Photometry, make a sensitive measurement of the amount of light coming from the asteroid and watch it over time in different over different months, or maybe over different days, or maybe even moment to moment. You can see small variations in the brightness that might give you clues about how the asteroid moves, because most likely it's not a perfect sphere. It's probably potato-shaped, as many asteroids are. And sometimes you're looking at the small end of the potato, and so you see a modest area that's reflecting sunlight back to you, and sometimes you're looking at the side of the potato, and it's kind of long, and there's a larger area that's reflecting more light. And if you watch this change, you can imagine that you're seeing more and less light over time as the potato rotates, and you can nail down the relative dimensions of the potato, the relative proportions of the potato, because there's a long side and a short side, and you can get you can make a fit to your data and have some guesses about this. This is on the left here is a shape model for Psyche derived from light curves, for photometric data, as I was describing. It is much harder to do radar observations of asteroids, especially distant asteroids, but it's been managed. After all, this is a pretty big asteroid, and it reflects radar reasonably well. So there are also shape models derived from radar studies, and the fun comes when the radar people and the photometry people have to get together and see what the differences are between their shapes and stuff. But what else have I got here? Well, you want to look at infrared light because because you can get that's the most interesting part of a spectrum for distinguishing asteroids chemically, and it's also possible if you go if you have a very, very cold telescope up on a mountain someplace, you can look in the submillimeter like the ALMA array and look at the thermal emissions from the asteroid, which gives you a clue about the thermal properties and helps constrain what the surface is made of, what it's like. Here's the numbers. Here's what we know about Psyche, sort of. It has a 240 kilometer diameter, more or less. Indeed, there's probably 3 numbers for its diameter in the different axes based on the shape model, but that's not on this slide. It is thought to be metal, first of all, because what we know of its volume suggests that it's high in density, and the density of iron is about 8 grams per cubic centimeter, and Psyche seems to be between 6 and 8, and that means there's a lot of very dense material in it, quite probably iron or nickel. The spectrum looks more like metal than like rock silicate, but it does look like it's a mixture. It doesn't look like it's pure metal asteroid like nickel iron meteor would be. So it's got some dusty or rocky stuff on its surface. It's very shiny in radar. It's good. The high dielectric constant and high albedo, radar albedo, mean it's very reflective of radio, which means well, another indication that it's sort of metal-like. And there's a high thermal inertia that we can tell from infrared measurements. And a nice thing about this main belt asteroid is that I guess if you've flown a few electric propulsion missions, very many of them have gone into deep space, but maybe if the JPL people are kind of jaded after enough missions, then they can say it's relatively easy access if you have electric propulsion. And here's the numbers. It's about 3 astronomical units, 3 times the Earth's distance away from the Sun, so a big wide orbit with and reasonably high eccentricity, but not a real high eccentricity. So it's a notably elliptical orbit. The inclination is about 3 degrees to the ecliptic, and we can say A is, if you are a kilometers person, A is 436 million miles in orbital 7 major axis, or if you're English, still stuck in the English system, it's 271 million miles, where we are 93 million miles away from the sun. The PI of the mission is working at the University of Arizona, right? Did I say that? Or anyway, she's in Arizona. Oh, or is it Arizona State? I should check.
Arizona State.
Arizona State, thank you. My mistake, alumni of Arizona State. So she has a slide comparing the size of Psyche to the size of Arizona, but she also gives talks in Massachusetts, so she has a Massachusetts diagram on this. It's about, the total volume of the asteroid is about the distance between Flagstaff and Phoenix, if you like, and helps you visualize things a little bit. Well, suppose these people are the winners of a struggle to get the spacecraft you want to fly flown, right? And you win this struggle by saying, we have science objectives. There are questions that we think we can get better answers for with if we fly a spacecraft there, and here they are. Is Psyche a core object, as I was sort of saying in the cartoon diagram I was showing, or is it possibly material that never has melted, but is rather dense and has all of these properties? There's possible scenarios where that could come together. Can we distinguish those two cases? Can we determine relative ages of Psyche surface? Just get some pictures of the surface, study which craters are on top of old or overlapping older craters that they disrupted, and other features of the surface that may show signs of having evolved, and try to build up a relative idea or a relative map of which parts are older than other parts, and that begins to tell you the story of how the surface evolved. Looking at what we can measure of the chemistry of the surface, that is, what elements make it up, and we fly some detectors that are particularly good at telling us how much sulfur and how much potassium, how much silicon might be in this composition. Those are important geochemical clues to the evolution of this once molten metal object. Okay, so we know something about the Earth's core, but we can't actually see it. It's thousands of miles away from us, and they're behind an impenetrable wall of rock, right? But it would be nice to know what we can learn about the chemistry of Psyche. If it is like the core of an evolved planet, the dense core of Mercury or Venus or Earth, then we'll have a chance to be studying something like a planetary core close up. And of course, make a map of the surface. That's always a goal, and it feeds to some of these other goals. How you get there? Psyche. I'm going to show you some outdated information, because it's the best set of slides that I have about this. Notice the sun and the orbit of Earth and the orbit of Mars as circles around the solar system. Psyche is much further away than Mars is. I guess probably twice as far from the sun as Mars is. It is. We can take our spacecraft and launch it from Earth. In this on this schedule, the original schedule, which has now been delayed, this thing says launch in August of 2022 and fly to Mars and use a flyby past Mars to pick up some of the speed you need and maybe change your angle to to get to the orbit of Psyche, and then cruise for a long time and in a gradually widening orbit until you get to Psyche, and then do what you can to reduce your speed relative to Psyche, and slide into a captured orbit around Psyche, and then start doing science for, in this scenario, 21 months, a little shy of 2 years, and with a 3.4-year cruise. And because the launch has now been postponed, the dates on this are wrong, but the picture looks about the same. Launch this fall and so forth. We'll have some of the dates on that in a later slide. The spacecraft is a partnership, or building the spacecraft is a partnership between NASA's Jet Propulsion Laboratory and Maxar SSL. Maxar has made many satellites, and they're particularly good at electric propulsion. Yes.
What will be the launch vehicle?
I have forgotten. I think it's a Falcon Heavy.
Heavy.
Yeah.
Okay.
And are there slide notes? No, there are not. Sorry about that. But what's notable here? Maxar is providing for Hall effect, so-called Hall effect thrusters that each one can produce about 1 ounce of thrust, or I think that's probably an ounce of them altogether. And JPL has provided a computer that's similar to the flight computer inside the Curiosity rover. They have experience with it. They know how to program one of these. It's qualified to live in space. So we're using some tried and true technology. Here's a nice picture where of a test where the spacecraft solar panels are spread. There is it 25 meters in width, total spread, and 3 meters high here. So something like 80 feet this way and something like 10 feet this way. And in a few depictions of Psyche, the mythological figure, she has wings. So, let's go with it. It's Psyche has wings. What the heck? What do you have aboard? There are only 3 instruments, but they will together address the science questions I was talking about. And there's always the ever-present ghostly 4th instrument, radio science, where you can use if you've built the communications system of the spacecraft correctly, you can also use it to do subtle measurements of Doppler shift as the spacecraft speeds up and slows down, and you can use that to help measure the effective gravity on the spacecraft, so radio science is really an extra instrument almost. But we talked about taking pictures. I mean, that's sort of the most obvious thing we all would like from a space mission. So there's a multispectral imager on board that that is compared to a Swiss Army knife here, I guess. Because this thing, the Psyche, the object, Psyche, the asteroid, is probably has a lot of iron or nickel in it, then there are probably there might have been events in its origin where it had a magnetic field or acquired a magnetic field, and making a measurement of a careful map of the magnetic field around it is a crucial kind of measurement. So there's a really good magnetometer on board, and finally there's gamma ray and neutron spectrometer for picking up emissions induced by solar cosmic rays or galactic cosmic rays on the surface. If something makes excites an atom of the surface material, it may decay from its exciting state and give off an X-ray, or sometimes perhaps some neutrons. And measuring the X-ray spectrum or the X-ray, the gamma ray spectrum, if there's anything radioactive in the material, in the heavy material this is made out of, then maybe that radioactive stuff will decay and occasionally send you out a gamma ray level photon. And all of these photons of distinct energies can be sorted out if you have a good instrument to tell you what kind of element gave off that particular photon. And so that is how you get at some of the chemistry, the chemical composition of the material in ways that aren't the same ways that the spectrum from a multispectral imager can tell you. And you put those different kinds of information together, and then argue about it with the other scientists. This mission is quite a lot like the Dawn mission, and I think that the Dawn experience, which is I think 11 years or so, gave JPL a lot of confidence that that another mission to orbit another large asteroid could be done with pretty similar, a spacecraft that has lots of the similar technology. And in particular, operational techniques, like how do you fly one of these things? Do you have some software that helps you with your operations and stuff? I think that was pioneered for Dawn. Dawn made a launched in 2007. It was also an ion-powered spacecraft. The blue plume suggests electric propulsion here, and it flew to Vesta and orbited Vesta for a while, and mapped out Vesta and told us a lot we didn't know about that large asteroid. And then it went on, it left Vesta in when? I don't know. Well, sometime after 2011, after a couple of years after 2011, it packed up and left Vesta and moved on to the queen of the asteroids, Ceres. And did the same job on Ceres. Nobody knew that Ceres had, like two bright dots that probably were the eyes of a giant creature lurking in a crater. Anyway, it was a swell mission, and now we understand something better about how to orbit an asteroid and efficiently do science there. The operation, imagine that Psyche has arrived at Psyche and is in some orbit around the body. Here's how things are going to work. The instruments will be studying and gathering data on the sunlit side, where you can get some pictures and such. And so on the sunlit side, it will be pointed down at the spot right underneath the orbit, the nadir. It'll be looking straight down and watching the landscape go past. But there will come a time when Psyche is passing by the night side of the asteroid, and at that time it's a good idea to point the radio dish at Earth and download the data you've gotten. Downlink, I guess, is the phrase in the space biz, and so that's kind of going to be take pictures on the bright side, send data on the dark side, as the mission goes on, sort of basic operation. And I'm sure there'll be variations on that depending on particular changes in the science plan, where maybe you need to keep getting data for a whole orbit for some reason with one of the instruments. And the whole operation, it's not going to simply be fly to Psyche, go in orbit, and then, do your science from there. It's complicated. One simple consideration is that the asteroid Psyche is not it's not a uniform sphere. It's not nice and spherically symmetric as many of the planets are, approximately. So that means if you're orbiting a potato, there are going to be wiggles in your orbit, right? Sometimes there'll be a lot of potatoes straight down from you, and sometimes there'll be less potato. And so it's a good idea to put your spacecraft into a distant orbit, and pretty high, where you can sort of ignore those irregularities, but also you can measure the irregularities very carefully. And once you have at least a rough map of the gravitational field, you can make better plans for sneaking your orbit down and going and getting closer. So there are different size orbits, and each one they'll be taking this data with all of their instruments in all of these orbits. But each one of these orbits has a particular way of giving an instrument a chance to shine. And we'll look at that in some detail here. Okay. So at the highest orbit, in the earliest time after arrival, that will be the best time to get magnetometer data get a global idea of the strength and direction of the magnetic field all over Psyche. And as I said, the rough gravity field will also be good for planning out future orbits. So that's planned to be 56 days, I guess, in the original plan here at 700 kilometers above the surface. When you go to orbit B, you'll be considerably closer, and that'll be a good time to get global imaging and start to make your map of the surface and cover Psyche's surface completely at pretty good resolution. You'll still be measuring the magnetic field. You'll still be taking doing radio science gravity measurement, but this is your best for getting your global map. You'll lower the orbit a few months later down to the purple one here, orbit C, and now you'll be able to get very fine detail on the gravity, and you'll understand how to maneuver the spacecraft safely and not be in danger of coming down or because you didn't account for all the wiggles in the gravitational field. Finally, when you understand the gravitational field very well, exquisitely, then it's time for the final orbit closest to the surface, which is obviously this will may give the imager a chance at much better detail. But it is the very best place for the gamma ray spectrometer to get to work. Ditto for the neutron measurements, because it doesn't give you very much information unless you're quite close to the surface. This is I'm going to give you without a complete briefing on this. I'll show you a couple of slides. Like in orbit A, the most distant one, 700-ish kilometers up. The one image from the imager will cover about this much of the imaginary asteroid that's been rendered here. So over one orbit, you can cover quite a large fraction of Psyche, and in 4 orbits, you can make overlapping pictures that can pretty much give you a complete global coverage. And then 4 days later, you got some more of that, and you begin to get a really. So this is great for photography, for imaging, right? But the gravity science isn't very high resolution, but it helps you plan lower orbits. And the gamma ray neutron spectrometer isn't very useful at all here. Down at the lowest orbit, skipping over a couple of these, here's a picture of what happens in orbit D, and you can see maybe why the imaging people, this is not their very best opportunity to study the asteroid, because while they can get great close-ups, one orbit only covers a rather thin noodle of the asteroid, and a day, even a whole day of imaging doesn't get, doesn't get all of the asteroid at high resolution. So you might have limited coverage, great pictures for a somewhat limited area. But this is terrific, as I said, for the gamma ray studies. Now, this was the plan was to build and launch this spacecraft last year, and in sort of the winter and spring of 2022. Understand that people were putting this together under COVID conditions, where it became much harder to work together and have everybody delivering all the parts on a timely schedule and testing stuff in the clean room and whatever. They were doing software testing, and in the spring of 2022, it became clear that there were difficulties cropping up with compatibility and stuff that needed to be ironed out, and it was going to take time to iron them out, and the time left before the launch window, the launch date, was shrinking badly, and they had to make a painful decision to delay the launch and until some later time. We didn't know quite when, and this was a serious matter. So NASA convened an independent review board to take a serious look at how JPL and the investigators were managing this project. Did they have enough people? Did they have enough of the right kinds of expertise? Were they trying to get by on too narrow resources? And in November of last year, they made a series of recommendations saying, listen, you got to get more of these kinds of specialists. Somebody should fill this vacant position. You need better communication, X, Y, and Z, management recommendations and stuff. So that was a serious setback, but the review board was recommending stuff that would improve things. And I can say that on the 5th of June of this year, which is yesterday, the review board met again to see how their recommendations had been taken up, basically to evaluate the performance of JPL and the Psyche project people, and they were fairly complimentary. So that it went well. The recommendations they made have been taken seriously and implemented, and the review board said, use the word outstanding. It said, the overall probability of mission success is high, which is exactly what you'd hope a review board would say about your project. And so that's kind of good news. So we're not on the original plan, but it's going well, and it's been blessed by an outside review board who thinks that Psyche is well underway. Yeah.
Does this review board calculate cost overruns, or is that another department of NASA?
It's kind of another department. The cost, the last time, the General Accountability Office, the GAO, the piece of the government that's kind of watching the budgets of everybody in the government, make studies of various things like projects, and I guess they have like an annual report on how NASA projects are going, and they said that the cost of this thing of Psyche project was estimated in the last report at about $1.1 billion, and that was a certain percentage overrun from what the original cost was supposed to be. But they also don't have completely up-to-date information about this new plan, so they cautioned that they're gonna, re-estimate that. Like, well, given the launch delay, it affects some things with the operation. Like, instead of a 21-month period, in order to meet all the science goals, the spacecraft needs to orbit for longer, because the lighting conditions, the seasons on Psyche are somewhat, we're going to be in a different season, so the nearly perfect alignment is not as good, and one pole or another is going to be mostly in the dark for some time, and it'll take longer to catch up and get all the see all the bits of Psyche they'd like to. So more months with more people working on with people working on the project all that time, that's going to be a higher cost, but nobody has yet estimated exactly what that higher cost is. That's the best answer I can give you, and it's not incorrect. It's not perfect, but you should. But the GAO is going to take a look at this sometime in the next 12 months or something. So there will be news if you care to know. There'll be more information about it.
And is there, I noticed initially when it was the October or the 22 launch, you said it was what, 4 years to reach it approximately?
Yes, it
Now
was
we're
like a
talking
3.5.
6 years?
Now longer, yes. Now we have a revised schedule, and I don't have all the numbers. Like, I'm not sure when the Mars flyby is going to happen, but there will be another Mars flyby. But it launches in a period of a couple weeks this fall, sometime. It will eventually arrive after most of 6 years at Psyche instead of a 3.5-year cruise, and the science operations will go for 26 months nominally. I mean, if you have a working spacecraft at orbiting an asteroid, usually the NASA will grant you, longer operation, but that definitely needs to be reviewed and budgeted for. So the operation may well be beyond 26 months, but it'll take 26 months to hit the goals and claim that the original objective has been met. Any other questions? Yeah.
Do you know how many orbits around the asteroid it'll be within a 24-hour Earth day?
Yes, that information is, which I glossed over completely, is back on a slide. Where's my pointer? Oh, it's on the other. It's over. Okay, let's put it here. Let's go back to the slide I'm thinking of. Click. Yes. So the answer to your question for orbit A is 32 hours, and the answer to your question for other orbits, because they're lower and the spacecraft is going faster and it takes less time to complete them, is 11, 6.5, 4.1. So you can do in these regions, you can do a bunch of orbits a day. Is that okay? Yeah.
Yeah, Bill, there's talk of mining asteroids. What is sometime in the future? What's your take on that?
Well, my gut feeling is I love the idea, and I've in the past I've studied it considerably, and I know people who have attempted various kinds of projects. There were a couple of asteroid mining companies 10 years ago, but they went belly up because it's really kind of premature. So I guess I am less excited about it at this date, having seen asteroid mining is still pretty far away. We still need a regime where everybody agrees that you can, or maybe agrees that you can't, grab some material from an asteroid and it's your property, and you can take it home and do stuff with it. That's an unsettled area of space law, and we have some some agreement on it, but it's a place where the people who make space law treaties and such things, have yet to make a very clear agreement there. And if the United Nations or treaties the United States have signed or what have you don't cover whether you're allowed to own the material from the asteroid or not, your bank is unlikely to give you a loan to build your spacecraft. It introduces an uncertainty with this kind of stuff, entirely aside from any of the scientific or technical aspects, that you really need a business climate where people understand the consequences and there's some confidence that, like, if somebody takes this risk, then what the risks are well known and so forth. I have some optimism that international legal regime and a financial climate that allows somebody to consider launching it or considering developing an asteroid mining enterprise or developing something like asteroid science is worth something, right? Nations pay for it, they pay their scientists to do it, right? Why couldn't a company fly something to an asteroid and sell the data to NASA or ESA or whoever wants to learn about that asteroid? A commercial arrangement to obtain data or do science might be a possible source of income without, or pay somebody to bring a sample of an asteroid back for scientific purposes. That is no longer as profitable as the dreams of asteroid mining to provide a space-going industry with raw material and build cool stuff like cities in space. But it would be a really good foothold to start. You asked me if I had any thoughts, and it turns out I have a lot of thoughts. Yes?
So the basic question I'm trying to answer is that there's two modes this thing could have originated. So one is through accretion of just floating iron and stuff out in space.
Mm-hmm.
And the other one is that it's the remnant of a massive collision with something that was a planet at one point that had a core.
Yeah, not perhaps a planet or anything as big as a planet, but let's say a series or a something bigger than series that was big enough to be hot and melt its core. So, what's the question?
Well, that was just. I did a Google of how many asteroids, or what percentage of asteroids are metal, and it's like 8%, so it's pretty small. But then, we're all made of iron. We are all stars, stars, so there's got to be a lot of iron out there, or metal, I guess. I guess I was trying to pick one of the two theories, and my current thinking is, if it was the impact of something big or bigger than Ceres, the likelihood is that's the small remnant of something bigger. Since we don't know, we don't see any other bigger pieces of metal out there, my thought is it's probably an accretion mode. Yeah,
there are other metal type asteroids, but they're smaller than Psyche. This is the biggest. Going out there to find out, to differentiate between these two theories, or it's probably like more than two, right? If you actually get geologists in a room together, but trying to distinguish between one scenario and another with the right instruments is major goals of the Psyche mission. Yeah.
Have they collected enough data to determine the rotation rate? of the
Yes.
asteroid?
The rotation rate is more or less easily obtained from the light curve. And
And what is that rate?
probably on one of my slides, don't you think? But I didn't notice.
I was late, so I probably missed it.
Yeah, I don't know. Let's go to the one that has all the numbers on it. But I don't recall it. I don't recall that slide having the rotation rate.
It's one asteroid day.
It's one asteroid day, indeed.
Psyche data.
Look, there's some fine print in here. What does it say? Nope. Seems like the kind of thing that ought to be on this slide. Also, it's kind of implied by the data in this slide. Which again, even the fine print doesn't tell me. So, if I went to the publications that this came from, it would be right there, but I'm sorry, it won't happen. That is a number I really should have brought to this talk. Yeah.
Bill, do you know if there's enough fuel to give Psyche a new mission, like Dawn and New Horizons both got a new mission?
Cool idea.
After the 21 months of science is done?
If it flies to where it's going and then does its orbits in succession and completes its science mission after a couple of years, might it leave Psyche with the remaining propellant it has and go someplace else?
Exactly.
My guess would be that's probably a pretty fair bet. In at least, I'll bet it's an engineering possibility, although I personally have no idea what other asteroids might be favorably aligned to reach from Psyche's orbit. But there probably are some. If this is a possibility at all, it is certainly in the back pockets of the experimenters, even perhaps now. That is something they look at, and something they'll certainly think about during the years of cruising. But they can't officially say that's our plan unless NASA has blessed it, and that really won't come until nearly the end of the mission when they're asking for an extended mission. Now, so an extended mission could keep orbiting Psyche and learn whatever more is to be learned, like, get perhaps smaller error bars on some of the concentration of minerals from the gamma rays, or on even finer, a couple more coefficients in the expansion, the polynomial for the gravitational field, or what have you. But, adventure, going off to see a whole new asteroid that hasn't been studied before, that's pretty tempting.
So it won't deplete its fuel.
What about landing on it? Well, we have at least one mission did that.
Electronic
What's it saying
It
here?
generates its own
It
fuel.
says, Psyche takes just over 4 hours to rotate once on its axis. Yep, thank you. It's been Googled. It's got to be true. Larry's, you got it.
That was what I was going to tell you.
Oh, I
Look it
see.
up as well.
Sorry to steal your thunder.
Doesn't it generate its own
Next time,
fuel?
sit in the front row.
Doesn't it generate its own fuel? It's electronic propulsion. It's got, if it gets sun to its solar panels.
There's a fluid that it's kicking out the rear.
Is
It's
that-
ionizing, and which is
Usually
xenon.
xenon gas is a lot of them used. I think Dawn used that.
Yes.
So there is a finite amount of
Right.
fuel.
So
used.
something can deplete.
There's a tank, and it has xenon in it, and
Yeah.
it gets used up. This is another detail I glossed over and didn't explain. Yeah.
Sorry, I was a few minutes late. There are thousands of asteroids probably in the asteroid belt. What's so interesting about this that NASA chose this?
This is one of the few that appears to be made of metal, or mostly iron, perhaps. If you know about meteorites, and you know that there are a lot of meteorites that have a combination of iron and nickel. Well, they're very dense and they're very sturdy, and when they make it to the ground, they don't look similar to other rocks. So it's easy to spot the iron nickel ones, and we have a lot of them in our museums. But actually, they're very much in the minority of the types of rocks that fall from space, and objects that are more like stones or more like lumps of coal, or some combination thereof, are more frequent, and the population of the metallic ones in the asteroid belt is actually pretty low, a few percent or something. So this is interesting because nobody has flown a spacecraft to an asteroid like that yet, and there's a bunch of interesting evolution of asteroids and evolution of planets questions that studying one of these guys could answer. Yeah.
The days in orbit on each thing equals 11 months. Are the other 10 months the travel time between the orbits?
2 slides ago where you had the 21-month day.
Let's go back to that.
And then the hours.
I don't think I've studied the arithmetic hard enough to answer that question, but the answers might be on that slide.
Further into
It's got to take a bath.
So you're asking about the period between orbits.
Well, it's a 21-day months of orbital science operations.
Mm-hmm.
Orbit A is 56 days, orbit B is 76 days, orbit C and D are 100 days.
Mm-hmm.
That adds up to so much divided by 30, that's 11 months. What happened to the other 10 months?
Your guess is correct that it takes some time for the spacecraft to maneuver, to sort of follow a spiral under the gentle thrust, 1 ounce thrust. Follow a spiral down to the next more or less circular orbit it wants to be in. And so there is some transition time, and that probably accounts for much of the missing time that doesn't add up in this picture. There might be other reasons that I don't know about. Like when they first get to orbit A, let's say, is there going to be a checkout period where they test that everything is working and they're not officially doing science, and that our orbit A science cruise begins on such and such date? I don't know.
I imagine a lot of the science will probably not be going on while the engine is operated, being there's no. So that I imagine the exhaust from the.
No, it's engineered so the instruments will pretty much work. Magnetometers are always tricky, and you have to kind of subtract the effects of having a bunch of electrical appliances aboard your spacecraft, or a big set of solar wings that are flowing electricity.
No, I mean while it's in the propulsive stage, transitioning from higher orbit to lower orbit, it's going to take some time.
I don't know.
They probably won't do that much, as much science observations during the powered flight of it.
Yeah, I think I don't really know the answer to this question, but I would conjecture, or for everything I've learned about the mission, suggests that they really will be running the instruments and gathering data, but that the nice circular orbits are probably where they would prefer to be gathering it. Also, you keep running your instruments, because what if the thing something breaks halfway through these procedures? You want to get as much information as you can, even if it's not the very best quality information that the complete mission would have provided.
Wouldn't you want to have a stable orbit to start with before you start probing anyone?
It's a stable orbit. Obviously, they want to have a nice orbit that that changes in a predictable way as they go here. But but much of the information is in the math. You could just, okay, we're partway between orbit A and orbit B, but the spacecraft navigation knows where it is and how fast it's moving and so forth. And if you take a picture from that point in the orbit, we could figure out what the spacecraft angle is, what the sun angle is, what part of Psyche the camera was looking at. And so that kind of stuff can be adjusted for. It takes, reasonably fancy software, but that's what they do have.
Still, what I'm saying is, you make one orbit, you take your measurement, make the next orbit stable, and it's different, then you gotta start to figure out why the difference in the measurement.
Yes, you're going to be making, it would be nice to make a map from a spacecraft that had, a reasonably circular orbit and went pole to pole over and over again. That's the ideal way to make a map, and every picture is approximately the same amount of ground, and you can overlap them nicely. But think about Europa Clipper, or about the passes that Cassini made to study Titan. Okay, Cassini could not orbit Titan out in the realm of Saturn, but it could visit Titan every few months and do a flyby and take some pictures and do other studies with its instruments and gradually build up. Okay, now we have one strip of Titan we've looked at pretty close, and then a few months later you return to Titan because Titan's great for doing Titan flybys are great for changing your orbit around within the Saturn system. But so there's going to be plenty of visits to Titan, but each one is a slightly different angle and probably a slightly different distance from the surface, and so there's lots of confusing, miscellaneous information and lots of pictures of different ground track sizes, and you just have to build up a map of as much of Titan as you can see out of those, different noodles of long, skinny noodles of imagery. So that, I guess, now that I've talked it out, figured this out while talking, I guess that would be my response to your question about nice, stable firm orbits. They're preferable. You could make a nicer study program with them, but if they have to, you got Cassini mapping Titan. And by the way, Europa Clipper is going to map Europa in just the same way. It's going to make flyby after flyby as long as the spacecraft is working of Europa, and it will not orbit Europa. Okay.
And just from the original the question, where do all those extra 10 months or 11 months goes?
Mm-hmm.
I'm guessing it's probably that time is probably going to be eaten up between the transition from orbit A to orbit B. Let's say it takes 50 days or something, and then 50 days, and say between orbit B and orbit C.
Yeah,
I think that's
pretty much.
You just can't point the nose down?
No, it's not.
Why not?
That's pretty much the conclusion that people in the second row came to. Okay.
It takes a while to trickle back.
You have a question.
Yes, I do. Okay, so so I'd like to ask certain questions. Do you think should be made, but aren't planned at the moment right now?
What asteroid missions do I think we ought to fly?
Yeah, you ought to make.
Wow. Good question. Probably more of the, orbit some more of the big ones, or some more of the big ones you could find that are different or weird. A mission like Lucy is amazing and is going to orbit sort of it's not going to orbit any asteroids, but it's going to do flybys of 11, I think, or maybe the number is higher because they keep finding objects along Lucy's path. So, you know, Lucy's a great grab bag that has a very clever orbit plan that takes in a whole lot of objects. And I think like a grand tour like that probably is possible, maybe even within the main belt. You know, we should have a few more missions to the Kuiper Belt if you'll count those as asteroids.
Yeah, that's also a good point too. And I do also, I guess, a follow-up to that. Okay, so it's like, you know, like unusual asteroids, do you think should be like, you know, studied in your opinion? They still haven't been explored yet.
Yeah, my mind is blank on this
Like
question.
Trojans and the.
Yeah, like I think that's
Yeah, Lucy is on its way to study the Trojans.
Oh, it is.
And it will visit both Trojan clusters, which is kind of amazing, and a few may belt asteroids along the way. I should do a Lucy talk, but I mean I have one.
What's the
but you know
tentative
we already have too many asteroids in this year's schedule.
What's the tentative schedule on this?
It's on its way.
Oh, it's already on.
Yeah,
Right.
It was launched in 2021, I think, and it will. It takes a long time to get to the vicinity of Jupiter this way, but you know, so it's kind of a more than a decade-long mission in all.
Maybe I should amend my question. When does it say again? What is it?
I've forgotten the date, but it's in some slides that I threw away in order to make this one. Yeah, I think I should probably wind down here because we have a meeting to get through. But I thank you for your attention, and let's all cheer when the Psyche spacecraft actually gets launched. Thank you.